Okay, folks, applications today. And these are the applications that came about in the last 20 years or so. Some of them really took off in the last 10 years, so you are at the cutting edge of spin physics research, including magnetic resonance. So you must have seen it on the BBC that the journalists keep crowing about something called quantum technologies. And in particular, you must have seen in various popular media, as well as the news, terminology being used like quantum cryptography, quantum computer, quantum control, and other things where the emphasis is very much on the quantum as opposed to what was previously there, which is colloquially known as classical physics. Now, these methods are fundamentally different from what we used to do in much of engineering, in that a bit in a classical computer can be either 0 or 1, true and false. But for quite a long time, actually hundreds of years, if you look at it, in mathematics, a logic was brewing of a rather different type, where a statement can be true, false, but also anything in the middle, indicating the extent of probability of a statement being true. And it was known as fuzzy logic, and it was a fairly niche area of mathematics. But with the arrival of quantum mechanics, it actually acquired a physical realization in that, as you know, in quantum mechanics, it can be in spin up, spin down, or in fact in any linear combination of the two, and that maps directly, at least superficially, on all that fuzzy logic mathematics. So the subject took off, hasn't delivered much as of yet, and there are good reasons to believe that some things will work and others won't, but I'll just let you judge for yourself. One of the recent things, in particular in NMR spectroscopy, is known as quantum optimal control, QOC, and it is about manipulating quantum systems with extreme accuracy. Subject is actually quite old in engineering, in that for classical devices like landing a spacecraft, for example, the optimal control problem has been formulated since the 40s, 50s, and 60s. For example, for landing the spacecraft on the moon, you would want to land with maximum possible precision, with the minimal expenditure of fuel, and certain constraints on all the intermediate steps, who says that the acceleration shouldn't exceed a certain value that humans are comfortable with. And so the task of maximizing a given outcome at the same time as minimizing various costs and penalties is called optimal control in classical engineering. And in quantum mechanics, it's formulated rather simply. If you have some initial condition, psi naught, some wave function that you know your system is starting with, what you'd want to do is to shift it to some other state, some destination state, we can call it sigma, with maximum accuracy, perhaps minimum time, or minimum energy, or any number of other conditions. For example, that the various pulses that you apply to the system should not exceed a certain amplitude, because your spectrometer cannot output the pulses of that amplitude. And so we'd like to do this, and then the measure of how well we have done this is actually quite simple. If we call it J, it will be a scalar product between our destination state and our initial condition, with all the evolution happening in the middle. So if that's our evolution operator, all the pulses, all the delays, all the decoupling, all the various things that go into the pulse sequence are collected into this U. Then if we have hit our target perfectly, then J would be equal to 1. If we hit it less than perfectly, then J would in general be some complex number, but it will be a complex number with the absolute values that is less than 1. So this needs to be maximized. or at least the real part of this needs to be maximized, because we don't really know how to maximize a complex number, because the metric is not defined on the complex plane with respect to which number is bigger than other, because it's two numbers involved. So typically what people say is they define J as the real part of the overlap between the evolved initial condition and the desired destination state minus some penalties. For example, if you exceed the certain amplitudes, then you would put a measure of that excess into here, and that will reduce your eventual figure of merit. So maximizing this and minimizing this is what optimal control is about. So how do we do that in practice? Well, imagine we have a Hamiltonian in the system that in an NMR spectrometer contains two things, two conceptually different things. These are the things you have no influence over, namely, for example, the magnet field. It will always be 600 megahertz. It's not realistic to change this in practice. Or J-couplings, they will always be there. We cannot do much about them. Or relaxation, or some other things that we cannot control, that cause dynamics whether or not we want it. Now, we inherited the term from classical physics. The term is called drift. H naught, let's see if it's an upper index, is called the drift. Close the window. Well, never mind.
No, you opened it.
Good? Yeah. Feedback. So, great. And then there are things that we can control, namely the amplitudes of various radio frequency fields. So typically these are electromagnetic things. In the mass spectroscopy they would be radio frequency fields. In EPR they would be microwaves. In optical spectroscopy, you know, some people smacking atoms with lasers, they will be the amplitudes of the laser beams and the corresponding phases and so on. So there will be a number of things we can control. There is a sum over n in here. These things will have amplitudes, Cn of t, and they will have the associated operators, Hn. So let's say in the case of a radio frequency pulse, this will more or less be the current that we put through the coil, and that would be the corresponding spin operator, Lx, Ly, or whatever it is that our coil is realistically influencing. So in such a Hamiltonian, and it would determine the system evolution, what we then have are things we cannot influence, but we also have things we can influence. Well, we know how our system evolves for a single quantum system. It's deep psi by at is minus I h of t psi. What we will now do is what most computer scientists do at various parts of the flow chart, is we will say, okay, if we have our control coefficients as function of time, so for example, this will be either c and of t, what we will do instead of assuming it's continuous, we will slice it into thin slices, at each of which we will assume the Hamiltonian to be constant, the so-called piecewise constant approximation. Now, of course, as soon as the Hamiltonian is constant, solving Schrödinger's equation becomes straightforward. You know exactly how to do that because we derived that. So psi of t plus some times of delta t is the exponential minus I delta t acting on psi of t. So for a piecewise constant Hamiltonian, at each little time slice delta t here, we need to simply exponentiate that, just as a computer to exponentiate this, and multiply it into the wave function, which is it. Or if we have the density matrix, then we will have two wave functions in here, and this will be double-sided, but you've all seen how to evolve this. So it is actually possible then to calculate the evolution, and let us write that J out explicitly. So our J will be, well, the real part of the destination state, and then this initial condition sign off. It will have the evolution from the first slice, so from this slice number 1, and we will call this exponential P1. It will have then the evolution from the second slice, and we will call the corresponding exponential P2. And on it goes all the way to Pn. Some really complicated formula. However, what is really useful here is that calculating, minimizing J is actually quite easy. Well, you know what we need to do in order to minimize or maximize something. We need to calculate the gradient of this, the derivatives, and then we need to step up the gradient if we are maximizing and down the gradient if we are minimizing. But the gradient is rather easy to compute. So our dj by d, for example, the amplitude of this C at time step k will be, well, the initial condition doesn't depend on the control sequences, the destination state doesn't, and in fact most of these p's do not. The only one that does, so I'll call this j, is the propagator of the jth slice. So what we will have in there is it will be the real part of sigma and Pn minus 1. Somewhere in the middle of Pj will occur, so dPj by dCj of Tk. And then on it goes all the way, actually should be Pk in here, and all the way to P2, P1, and then sign off. And that's just a derivative of an exponential with respect to a parameter. So the amplitude of the pulse at time slice k here. So you can take my word for it that these things are easy to compute. It only became easy like 4 or 5 years ago, but it's doable. And as soon as we have this, from here we have the gradient of J, and then our C, where are they? Wherever, Cm of T, are simply mapped into Cm of T plus K times the gradient of J. So we step up or down the gradient, and we maximize or minimize that function. Now, because a gradient is involved and we are effectively designing pulses, this is called gradient ascent of engineering rate. And you can probably see that this is a generalization of the composite pulse. Marcel has told you about composite pulses, the pulses that are designed to compensate their own imperfections. And optimal control is actually a generalization of this to an arbitrary number of pulses. Now, what is possible to do here is, firstly, of course, the level of accuracy in reaching the destination greatly exceeds what humans can realistically design by hand. So we have just taken the entire pulse sequence design process and we have completely automated it. So no inept, no NOE transfers, no complicated decoupling schemes. This is pure brute force numerics. You declare your initial condition, you declare your desired destination state, you declare the constraints that you have, press the button. Optimization runs. You typically get something in reasonable cases to the tune of 6 nines accuracy into This is also resilient to practicalities like the instrument, for example, not having a terribly uniform magnetic field. Previously, we had to use spin echoes and refocusing and so on. This numerical optimization will take care of that all on its own. It will evolve into a sequence that's resilient to such things. We might have a distribution of B1 fields, like where realistic coils do not have uniform B1 fields. They would have tilted different areas of the sample by different angle. These things can be designed to be resilient to that. Ultra broadband pulses can be designed that excite much bigger areas of the spectrum that would never be possible with RF pulses, and so on and so forth. So this is the current state of the art in magnetic resonance spectroscopy, is that by the time we run out of ideas about how to create a system by, an experiment by manual design, for example, in quadrupole spectroscopy, that's often the case, we have to subcontract it to a computer. So a practical consequence of this is out of gray, we get very accurate pulses, which are very accurate transformations of this system's state space. And this becomes important in the next section. Okay, so this is still magnetic resonance. Sophisticated, with a big supercomputer, very accurate, but still magnetic resonance. Something that technically involves spin, but isn't actually magnetic resonance, is called a quantum annealer. Now, here we have to begin rather far. Imagine a function that's not a function of continuous variables, but a function of discrete ones. Say f of x1, x2, and so on, xn, where the individual variables are not continuous, but rather have discrete values. For example, they can only be integers, or some such, or they can be the states of multiple switches. So you have a great electrical switchboard, and you would like to maximize something about the performance of the instruments that the switchboard controls. And then you can either throw or you can click up the switches in there, and for some combination of the switches you will achieve your optimum. However, there is no gradient because this is not differentiable. And in fact, if a particular position of the switches is good, there is in general absolutely no guarantee that any adjacent positions of the switches will be any good. And so you are faced with something called a combinatorial optimization problem, where no amount of tinkering, no mathematics, heuristics, nothing would actually give you any idea about which direction to move or which switch to flick next to improve it further, or whether there may even be a switch to flick next to improve it further, because there could be local minima, right? Amongst all the horrible combinations of switches, there will be just one that would just be awesome. And of course, unless you exhaustively search every possible combination of those switches, you will never find it. So these combinatorial optimization problems are exponentially hard. That is, if that has two possible positions, two switches have 4, 3 switches have 8, and switches have 2 to the n positions. So in discrete cases, O of 2 to the n complexity. Meaning in practice that if you've got 20 switches on your board, game on. But of course, problems of exactly this kind occur in financial portfolio analysis. Do I keep a certain asset or do I dump it? Do I sell or do I purchase? In various, well, I've already mentioned instrument engineering, but also in machine learning, in circuit resilience analysis, in semiconductor engineering, and so on. there is a number of really high stakes situations where you would rather want to know what is happening in here. So, one of the earliest applications of quantum devices has been to the problem of this kind. So many such problems, not all of them, but quite a few, can be mapped into the following. If we have a Hamiltonian with a lot of Zeeman interactions, so let's say sum over k omega k in the x direction, L x k operator plus omega k in the y direction, y k plus omega k in the z direction, z k. So these are all the Zeeman interactions. Let's say you've got the three magnetic fields in the three principal directions. And then let's put some j values. Sum over n less than k. 2 pi j and k, and then you would have the usual xx plus yy plus zz. So L x n L x k plus L y n L y k plus L z n L z. This is just a giant nuclear magnetic resonance Hamiltonian, right? The hats on all the operators. So the funny thing is, a lot of these problems, including things like financial portfolio management, are actually mapped to a very simple question. We need to know the ground state energy, and we need to know the ground state wave function for this. And minimum energy of this Hamiltonian corresponds to the minimum possible value of this, maximum to the maximum one. And then the configuration of all the spins, remember spin can be up or down, corresponds to the configuration of those electrical switches that you have to flick in order to achieve this minimum energy. So this mapping existed for a long time. It was known for a while that such problems exist, but of course, the difficulty, again, is if we are trying to do this computationally, the dimension of this Hamiltonian matrix is also exponential of the number of spins. As you know, it's actually exactly 2 to the n. And then the task of building this Hamiltonian and then calculating its lowest energy is, in fact, exactly the same complexity as the task of flicking all the switches manually, all the 2 to the n times, in order to find the minimum energy. What, of course, people then thought is, why don't we make a device that would do this, but experimentally? We will find that mapping, we will construct a spin system with exactly such J couplings and exactly such Zeeman interactions as to match our portfolio optimization problem. And then we will take that molecule, we just freeze it in liquid helium, it will collapse to its ground state, and we read it out, and everybody's happy. Well, but of course, as chemists, you can see the obvious problem with such a proposition is that it's next to impossible to control J couplings in an arbitrary way. You know, you only have a palette of J couplings. So all these quantum people have turned up at chemists' doorsteps and say, can you synthesize a molecule with arbitrary network of arbitrary J couplings? Well, chemists told them where to go. So anyway, various attempts have been made, but ultimately the spin people have failed to produce something like this. But the people who didn't fail to produce were the people who did superconducting quantum interference devices. Now imagine we have a loop, just a copper wire in liquid helium. Copper will be superconducting, and it will be really, really cold. As you know perfectly well from your ordinary quantum physics, when you have a particle on a ring, I think Crystallization must have considered that, that particle is quantized. And so actually the current in this loop is quantized. That is, it can be 1 unit of current clockwise, or 2 units of current clockwise, or 3 units in discrete quantized increments. And then, of course, there also can be currents that are counterclockwise. in various quantized increments. So what they said is, they said, okay, let's not consider multiple units of current. Let us freeze it down to the extent where, you know, we only populate unit of current clockwise and unit of current counterclockwise. Well, of course, this is exactly equivalent to a spin, mathematically. Current clockwise corresponds to spin up, current counterclockwise corresponds to spin down. So suddenly we have something that behaves like a spin, but can at the same time be controlled electrically and actually built on demand. Micro-manufacturing of copper wires is a well-established technique. You can basically just print on some circuit board. But then, of course, the J couplings between currents in a loop are basically capacitors. You connect them with capacitors, you tune the capacitance, and there's your J coupling. And so it's actually possible to create coupled arrays of microsquids that would mimic exactly this Hamiltonian. With restrictions, right? It's not everything to everything connected, it's a rectangular grid of these little loops, like this. I'm simplifying somewhat, but you get the idea. And then there will be some electrical interactions between them that will look mathematically like J couplings. Of course, not everything to everything can be connected. Here we don't have enough spatial dimensions in the three-dimensional world. Typical such chips are flat. And then there are limits as to which magnetic fields you can apply in a realistic instrument. So normally the devices can do at most 2. So you can have the Z and the X. And the coupling, I think, is only ZZ. So this can be done electrically. This can be done, and that can be done. That turns out to be enough to map quite a few of those discrete optimization problems into this Hamiltonian. And then, of course, you take this array of microsquids. This thing is a few millimeters across. It has hundreds of these loops with tunable junctions. You put it into liquid helium. You put it into an enormous Faraday cage to shield it from even the Earth's magnetic field, because these interactions are weak enough that the Earth's magnetic field is enough of an interference, or some passing heavy truck, goodness knows what can happen magnetically right around your laboratory. Just the wires. There's 50 hertz, a pretty serious magnetic field by the time you're doing these quantum current loops. Anyway, so you make these devices about the size of a small room. It costs a couple of $1 million, but it exists. It's called the debate machine. So the way that thing works is you take your optimization problem, you encode it first into more or less a spin Hamiltonian. But since the spin people couldn't do it, you have to rely on what the electric people did, which is more or less a spin system. Then you encode all of these J couplings into those junctions, and you do that in a few steps. So you start with just Z9. So no couplings. The reason for that is we really want the initial state of the system to be simple. And if we don't couple the electrons or the currents at all, then what's going to happen is basically all the currents will just go spin, and you will get a ground state that you actually know. Then at the point 2, slowly fade that Hamiltonian, so let's put Hz slowly, and it's important, Hz out, and fade the full H, the problem Hamiltonian, in. The process that happens when you do that is called adiabatic evolution. There is a very fundamental theorem in quantum mechanics that says if you begin in the ground state, which we do know we are in, and then you change the Hamiltonian really slowly, much slower than the reciprocal energy separation between the adjacent energy levels, then the system will stay in the ground state. And so you crossfade these Hamiltonians. If you do it slowly enough, you are guaranteed to arrive at the ground state of any actual Hamiltonian that your problem is about. And then item 3, I'm simplifying a lot here, I basically read the answer. The whole process is called quantum annealing. The origin of the word perhaps merits a bit of a discussion. You know, the original annealing a very long time ago was when a blacksmith took some piece of metal, heated it up, and then let it cool down really slowly. Right? So when you temper steel, you put it into water fast, so that the crystallization process of all those grains of iron carbide and iron proceeds in a certain way, and you got a particularly hard piece of steel. If you'd like to reverse the procedure, you slowly cool the steel down. That was called annealing. And then mathematicians took that for classical optimization processes where they would run some calculation in a state of a very high effective temperature where lots of states are populated, and they would computationally just cool the system down and hope that it ends up in the minimum state. So simulated annealing is an actual optimization technique in mathematics. And then when we went to quantum annealing, we kind of went the full circle, and we're not blacksmiths, right? But it's basically a piece of metal that has current in it, and we've had it at room temperature, and then we slowly cool it down to liquid helium, and then we do things to it. And so this quantum annealing process is actually going back, you know, to blacksmiths and swords. Anyway, now, for quite a long time, if you read the literature on the D-wave, the people who dealt with spin physics, the academic spin physics community, was rather skeptical about the claims these guys were making, because, well, it's a commercial company that didn't have any obvious links to any of the established initiatives in all of this quantum technology, but they persisted. And 20 years down the line, it's the academic community that delivered nothing, and these guys are selling these things like hotcakes. So there's an optical version of the same. You can do it with optical parametric oscillators. They're called coherent Ising machines, and various other types. But these annealing devices are real, and they're used by real companies, at least at the exploratory level as we speak. You know, people like Google and Microsoft and so on. In particular, because they guarantee, to a probability, but still, a global optimum. If you are training a neural network, if you're designing a semiconductor circuit, it really is useful for a semiconductor company to know that this particular configuration is a global optimum. Because as soon as this is the global optimum, that's it, you're done. There's no further improvement, even if you throw an extra $1 billion at it. So it's really helpful from the point of view of financial planning for a company like Intel to know that this particular circuit of some electronic logical gates that do a particular operation fundamentally cannot be improved upon. So they're using that to an extent at the moment. And we are literally seeing things published daily on this. So I'm an associate editor at Science Advances, and so we just published a paper that does computational analysis of these things. So this is current physics. Okay, now notice that although this technically with a bit of a stretch can be called a quantum computer, because it well does a certain kind of computation, and there's quantum mechanics kind of involved somewhere, it is not a general purpose quantum computer in that there is no flow control, there are no for loops, there are no if statements. It cannot be programmed in any conventional way you can think about it. The only thing it can solve is a certain type of optimization problem. So it is a quantum circuit, you could say. It is a quantum device. but not a universal quantum computer in the same sense as the thing that sits on your desk is a classical computer. The mathematical criterion for what is a universal computer was formulated by Turing, and it involves, well, it's quite an involved definition, but essentially in order to be a general computer, a device must be a Turing machine. It must satisfy all of these Turing conditions. So the next item in our lecture is about the states ZR. That is, how close are we to a true universal quantum computer? And the answer, unfortunately, is A, we're nowhere near, and B, there are serious doubts that this is ever going to be possible. And doubts are at a very fundamental thermodynamic level, as in the same level of doubts as there are about perpetual motion machines. That there's a significant school of thoughts, so that things are not supposed to be possible to begin with. Okay, so we would need first to define, well, not define, but perhaps sketch very roughly a quantum Turing machine. So a Turing machine, and I'm again simplifying grossly here, you can find it in computer science textbooks, but it's supposed to have a set of states. And in a classical computer, that's a discrete set of states. Let's say we have a computer with 8 bits of memory, and each bit can be true or false. So it will have 2 to the 8, 256 possible states, that computer. And then there will be some internal state that specifies the point of execution. So the set of states of a classical computer is finite. And at the most basic level, it will be true or false. 0 and 1, the stationary eigenstates of a classical computer. Of course, in the quantum case, you know perfectly well that superpositions become possible, and so a quantum device can exist where alpha squared plus beta squared with moduli here is 1 because of the normalization condition. So whereas in a classical bit we had only 2 possible states, for a spin, otherwise known as the quantum bit, we can have a continuum of possible states. Which is already kind of curious, right? Because theoretically, at least, that's a much bigger storage than this. If you have a dictionary to hand about what each linear combination means. Then the second thing that's required of a computer is transformations. Logical gates in the case of a classical computer, if 2 bits are both true, then the third bit is true. If 1 bit is true, the other bit is false, then the third bit is false. So all of these things like AND, OR, XOR, and other binary logical operations or unary logical operations, essentially Boolean algebra, must be present. However, such things, they're called logic gates, must be generalized for the situation where we have arbitrary linear combinations. So instead of an operation acting on 2 inputs, we have things that transform the entire state space. So you would have some operation acting on the wave function. And for example, if it's a NOT operation, then a NOT, quantum mechanical, acting on alpha 0 plus beta 1, will flip both. It will be alpha 1 plus beta 0. But these are in general matrices, more specifically unitary matrices, and therefore exponentials of some Hamiltonians. So that actually must be, because it's an evolution operator of some wave function, must be an exponential minus I h T some. So we would need to concoct some Hamiltonian and act it for just enough time on some wave function to effect this transformation. Now you can see we are hitting exactly the same problem as we were hitting in the case of the annealers, in that nuclear spin systems cannot be designed, not realistically, at least not on the synthetic organic chemistry level. You can put an array of them into some isotope depleted semiconductor and so on, but then you have a problem that single spin readout is singularly hard to achieve because the sensitivity is so low. You have to do it optically and so on, so exceedingly difficult. Again, the squid people have no such problems, and so it is quite likely that any practical device of this type is not going to involve spin. But the difficulties with this don't stop there, so I'll just list you all of them. So, as I already mentioned just now, it is very difficult to create such Hamiltonians and therefore such exponentials. So, problem number one, hard to create gates. Because the classical computer had just 0 and 1, but the quantum computer, each gate has to transform the entire state space of the system, or at least, leave it where it was. And doing this with extremely high accuracy is very difficult. Optimal control theory helps. But of course, because these operations are multiplicative, any errors would accumulate exponentially. 20 gates later, you've got no signal left. Right? So very hard to create those gates. Second problem is, of course, any such device must begin from a well-defined initial condition, which must be the ground state of the spin system or any other well-defined state. This is also very difficult because in the nuclear spin case, that temperature is in the millikelvin, very hard to do. In the electron case, it's liquid helium-ish, still difficult. And then if you want to get states other than the Zeeman ground state, you have to do optical polarization and so on. A rather exotic instrumentation. But the bottom line is hard to initialize. A computer must start computation with a well-defined initial condition. It's hard to even get that initial condition in a quantum device. Then item 3, the connectivity of the state space. It's a subtle point, so connectivity of state space. Let's say some gate requires us to take the transverse magnetization of some spin, S plus, and convert it into a 3-spin correlation. So like S plus MZ and Z, with 2 other spins. You know perfectly well how such things happen in the product operator formalism, but you also know that the universe only has 2 body interactions. That is, there's no such thing as a 3-body dipole coupling, only a 2-body dipole coupling. And so you can only add 1 operator at a time. So some J coupling will correlate you into S plus and Z, and then you'd have to sit and wait for some other J coupling to get you in here. But whilst that other J coupling gets you in there, the previous J coupling will be busy rotating you back into the original state. So you can see the controllability problem here becomes interesting. Again, optimal control comes to help, but the problem is that there are no direct paths between most of the states in the state space of any quantum system, because realistic interactions are 2-body interactions. Unfortunately, the sort of gates that you need for realistically useful quantum algorithms imply all-to-all connectivity in the Hilbert space, which is plainly not available. They can be synthesized through, multiple sequences of 2-body gates, much like an NMR pulse sequence works. And in fact, much of all this quantum computing business has been literally copied from magnetic resonance spectroscopy. Of course, the NMR people were pointing and laughing as that was going on. But basically the connectivity is not all-to-all, and furthermore the connectivity is really sparse, one extra particle at a time, more or less. That becomes a problem because of the fourth phenomenon, and that's relaxation. Whilst you are painfully trying to push yourself through the Hilbert space in the direction of some state that you're going to populate, relaxation is going to get you. And remember again that the speed of travel between these states is proportional to the interaction. Right? So compute rate is, roughly speaking, proportional to J, whatever generic coupling you have in there. But the relaxation rate is proportional to delta J squared, where delta J is the modulation depth of that coupling by some external noise. External noise is unavoidable. You have to cool the system down to absolute zero, but even then there are zero-point vibrations. You know that it's not actually possible to get rid of them. And so there will always be this modulation that will be relaxing your system at the rate that is in principle quadratic with the interaction amplitude, assuming that you've got spatial degrees of freedom that are much stronger than the spin ones. Anyway, so this is a fundamental contradiction in that when you introduce an interaction, you also introduce the associated relaxation. Given the finite speed of travel in the Hilbert space, that relaxation is going to get you before you have an arbitrary Hilbert space transformation. Now, of course, what is natural here is to say, okay, well, relaxation is the exchange of energy with the environment. Why don't we put the system in high vacuum, freeze it to absolute zero, stick it into intergalactic space when there are no gravitational, electromagnetic, or any other interactions of any kind? So the system that is perfectly insulated from its environment and doesn't dissipate energy into it is known as a perpetual motion machine. More specifically of the third kind. Remember, the perpetual motion machine of the first kind is the one that gives you energy out of nothing. The perpetual motion machine of the second kind is the one where effectively the heat is transferred from the cold body to the hot body without anything else happening. And the perfectly insulated one is the third kind. And so you could say that the very task of trying to build a device like that is doomed in a sense that much like it happened in history, you know, in the 19th century when perpetual motion machines were all the rage, by carefully lubricating and suspending and evacuating the air, you can achieve perpetual motion. However, it is not possible to extract any infinite energy out of it, or in fact to create a fridge that wouldn't consume more energy than it pumps across. And so the task of getting a quantum system going so it would compute something by its evolution process rather implies that you are able to keep this at bay. And of course you can do it incrementally. You can find a machine that relaxes slowly enough for some calculation, but the moment you increase the size of the calculation, the machine would have to relax even slower to enable the calculation to happen. And you can see the same kind of catch-up game as the early designers of ordinary perpetual motion machines had with friction. In the case of those, this was called friction. Now it's called decoherence, but the principle is largely the same. Now, item number 5 in here is also philosophical in that, you see, after 30 years of trying to make something like this, people have rather dramatically failed, despite millions of pounds of expenditure and thousands of people working on it. So there's a significant school of thought that doing what these things are trying to accomplish, namely solve exponentially hard problems with polynomial resources, might not be possible to start with. There may be some fundamental prohibition within reality or thermodynamics that we are not yet fully aware of that prevent us from ever doing this. Because otherwise, you know, the amount of computing power that this has will be in contradiction with some properties of the universe that we have to deal with, something like Lorentz invariance. So it's possible entirely that some fundamental law entirely prevents machines that solve exponentially hard problems in polynomial time from becoming possible. So this is literally, so I've kind of ramped you and dropped you into the state of the art. This is where we stand at this minute. And these are the papers that I'm receiving for review and so on that are struggling with this exact topic. Anyway, so some quantum technologies are well developed, like optimal control theory. Really works. Just press the button, it will do it. Other devices have just entered the market, like the D-Wave machines, get it, a Coulomb, an icing machine, and or the various simulators that do them. But it would seem that the kind of quantum computer that would crack the prime number-based encryption or something like that is not going to be possible unless, if it's even possible, there's a Manhattan project scale funding attached to it. So these are very, very difficult things. At the level of the nuclear fusion and perhaps fundamentally impossible to start. Any questions?